Hi guys, Dr. B here. This is a new way to do Lewis dot structures. This is called the V's up method. So what does V's up stand for? So it's an easy way to do Lewis dot structures. So valence electrons, skeletal structure, used, like how many electrons are used, and then lone pairs, meaning the electrons are going to be involved in the lone pairs somehow. So you redistribute any remaining electrons, like I said. And then if they're not enough to complete valence shells, then you move lone pairs to make double or triple bonds. You check that all atoms have complete valence shells of 8 valence electrons, or 2 for hydrogen, including lone pairs and bonding electrons. Check your work and make sure that your electrons equal the number from step 1. So for example, this V's up here for CO2, carbon dioxide. It's easy, but so valence V's up. So remember valence electrons, you have 1 carbon, so it's 4 valence electrons plus 2 oxygens, which is 6. So that's going to be a total of 16 valence electrons. The skeletal structure, you put your central atom and try to draw out your bonds as far from each other as you can, because remember, there's our electrons, they have the same charge, so they want to repel from one another. Then you used up 4 electrons, you subtract 16 minus 4, you have a total of 12 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Whenever you are putting these on, make sure that you start out from the outside, work your way in. So we can see that oxygens both have 8 valence electrons, but carbon only has 4. So let's take one of these lone pairs. Doesn't matter which one really. Let's just take this one here and put it back over here to create a double bond. Same thing on this side. We'll take this lone pair, make it part of a double bond because carbon had not had its full valence shell just yet. So double check if you have 8 valence electrons on each atom, and we do. So the final Lewis dot structure is C, double bonded to an O on either side. So V's up. Boron is 3, fluorine is 7, so 3 plus 3 times 7 is 24. Skeletal structure, central atom. We used up 6 valence electrons. So 18 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Remember that boron actually is one of the exceptions. It can't have a full valence shell. So it would be just 3 bonds. I mean, it can't have a full octet, I'm sorry. So with its 3 electrons, it can only share with another 3 to make 6 total. So this is all we have to work with. Ammonium ion V's up. 5 plus 4 times 1. This plus sign means we lost 1 electron, so minus 1. That is a total of 8 electrons present. Skeletal structure. We used up 8 electrons. We have no more lone pairs. So because there's an electron that was lost, and then you have an ion, you have to put brackets and put this sign on the outside. The sign with the car charge and all that. CS2 V's up. 4 plus 6 times 2, 16. Skeletal structure, same as CO2. We used up 4 electrons. Left over 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Moving this one over here to create a double bond. This one, move it here, create another double bond. So left over you have C, double bonded to two S's on either side. And they all have their 8 valence shells, 8 full octets. Okay, sulfur hexafluoride, V's up, plus BV, 6 plus 7 times 6, 48, looks like. Yeah, 48. And then we have our skeletal structure. There you go, to make it look nicer. 2, 4, 6, 8, 10, 12. Wait, 2, yeah, we used 10. Oh, so we used 12, I'm sorry. 6, 3, 36. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So it looks like we can't really do anything else, so we're good. Remember, sulfur and basically elements that are in the third orbital and beyond, they have a potential for an expanded octet. So sulfur can do that, but oxygen can't do that. Chlorine can do it, but fluorine can't do it. So ClO3 1 minus is a chlorate ion. V's up. 7 plus 3 times 6 minus 1, so it means plus an electron. Total of 18 plus 7, 26. Skeletal structure. Total of 6 used, so 20 left over. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oops. 19, 20. Not 1920, but 1920, you know. So we have to keep this for now, because this may not be the best structure, but we have to talk about something before we can get to that. So formal charge review. So the formal charge equals the number of valence electrons present on an atom minus the number of lone pairs plus bonds connected. So when I do that, I mean, technically, if you want to be mathematically technical, number of valence electrons minus the number of lone pairs minus the bonds connected to it. Sorry, I had to reconnect my charger thing, my bad. When you're drawing out the loose dot structures for some molecules and polyatomic ions, there can be several ways to draw this. You have to use formal charge because it helps you determine which one is more valid. The sum of the formal charges of each atom should add up to 0 for a molecule or add up to the charge for a polyatomic ion. The formal charges as close to 0 for all atoms is the most valid. So there will be no formal charge, quote unquote. If you have to have a negative formal charge, it's best to place it on the most electronegative atom. So ozone, O3. So V's up. So 3 times 6 is 18. Skeletal structure. Oops, so see. We used up 4, so 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, so now our oxygen in the center now has a lone pair. Okay, that's cool. Go for it. Whatever, no big deal. So we're gonna have to do this a couple of different ways. So I will make my central oxygen my oxygen 1, and then 2 and 3, because I want to focus on making sure that the number 1 oxygen, the one in the center, has its full. Actually, let's make sure it has a full octet. It doesn't even have a full octet, so we don't even have to do this, but we'll double check. So let's see. So this has 2, 4, 2, 3, 4, 6. So let's take this one here Move it over. So that creates a double bond. Now they all have 2, 4, 6, 8 valence electrons. Okay, let's just kind of do this then. Okay, then designate oxygen 1, 2, 3. Oxygen 1, get the formal charge. So it is the number of valence electrons on that atom, so 6, minus the number of lone electrons, 2, plus the number of bonds connected. So it's 1 plus. Okay, let's try 2. 6 minus 4 electrons in the lone electrons attached, plus 2 bonds connected, 0. Good. Let's try 3. So 6 minus 6 electrons plus 1 bond minus 1. So that means that based on the structure, it has it's the more electronegative element. We put it on that minus 1, so good. However, you'll notice that technically if you put this double bond I'm trying to put in a circle on this other side and flip with the single, technically you are creating a resonance structure here. So let's put my final answer. This is my final answer. It will be in the corner up here. You don't put brackets because these are not ions. Ooh, interesting. Okay, not bad, not bad. A carbonate ion. So what do? We use up. So 4 plus 3 times 6, 2 minus means I gained 2 electrons. So that's a total of 18 plus 2 plus 24. Skeletal structure. Used up 6 electrons. 18. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. Oh, should not want to do that. My bad. So let's see. Our carbon unfortunately does not have a full valence shell. So we can take this one here, put it there. I'll rewrite it, I'll erase it so that I need space. So I'll erase that. Don't erase it on your paper, just FYI. Cool, cool, so cool. Okay, well, carbon has its full valence shell, so do the oxygen. So we probably need to do our formal charge checkup. So the carbon, so this one right here, this will be that charge. This oxygen, sorry, yeah, right. This oxygen, the double bond oxygen will be this red star. Make it blue, I guess. And these are the same right now, so that will be the same for that. Let's see. I want to make sure that I have the right formal charges. So let's do this carbon. So carbon is 4 minus no lone electrons plus 4 bonds, 0. Good, it's perfect. This double bonded oxygen, it has 6 valence electrons minus, even the same color? It's not even the same color. Okay, I'll just change it here then. Cool. 4 plus 2, ooh, another 0, nice. Purple, we have 6. 6 lone electrons plus 1 bond minus 1. But there's 2 of them, so that is actually 2 minus. And because that's our most ideal structure. But because of this ability for these to alternate, we have to create resonance structures. Yay! So I'll do my best to make this as painless as I can, but I can't promise anything. Anyway, maybe I'm just complaining because I have to do it, but it's cool. So if I keep, and then I'll just draw this one up here. Oh, I can do it. I can fit it. I can fit it. Hope this won't be too big. I don't know. Hold on. Oh yeah, there it is. And then, oh, let's go. Cool. Oh, cool. I did it. Nice. Ooh, that was a lot. Resonance structures, formal charge, all taken care of. We're good to go. Hydrogen cyanide. Let's see. So I was going to say fangs up, but bees up. So 1 plus 4 plus 5 based on that formula. So 10. My bad. Skeletal structure. So remember when we're doing these, hydrogen is a terminal element. Carbon usually likes to be in the middle, like all life on Earth is based on carbon, so we'll go with that for now. So I used 4, 6. Well, I can't put any on oxygen. Only one I can really put it on for now is nitrogen, because 1, 2, 3, 4, 5, 6. So carbon, excuse me. Carbon. Let's see. Carbon has 4 electrons. Hydrogen's fine. So I'm going to do this. Replace these, because if you look, if I only did the one in blue, I would still only have 6 valence electrons. So I'm going to take this other one and put it there. That creates kind of a triple bond, so I'll make it nicer over here actually. Okay, well let's see. Double check our valence, formal charge, I'm sorry. So hydrogen, 1 minus 0 plus 1, formal charge is 0. Carbon formal charge, it is 4 minus 0 plus 4 bonds attached, 0. Nitrogen. Minus 2 plus 3. Ooh, nice. We're good to go. And there's no resonance here because you can't flip. It's not like you have the same element. You know, you have all 3 different elements, so you can't do that. So that's it. So if this is our chlorate ion type of looking structure, not really because it doesn't have a charge on it yet, but we have to determine the best Lewis dot structure for this. Include any resonance structures, blah, 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 blah. Take formal charge into consideration. So let's see. Right now, on this chlorine, we have 7 valence electrons that we have on it, minus 2 lone electrons, plus 3 bonds is 2. Well, I don't want that. I want them to be 0. So maybe we can try taking this one, creating a double bond here. So let's see how that would do. So 7 minus, on the chlorine we have, again, 2 plus 4, 1. 2, 4, 6, 8, 10. Let's see. Okay, well, let's see if we can take another another lone pair, make it a double bond. Okay, well, maybe a little weird, but let's see. So 7 minus 2 plus 1, 2, 3, 4, 5. Oh, shoot. So apparently this is the most stable structure. Ouch. So then let's just rewrite this to follow suit, make sure it's all good to go. And then if you're curious why, expanded octet. That's all you gotta know about it. Okay, so then if this is the best for chlorine, I'm sorry. Oops. So we got to double check the valence the formal charges. Let's do double bonded oxygen and then the single bonded oxygen. Oops, I'm missing it out there. So 6 minus 4 plus 2 is, so that's going to be 0, so 2 zeros, good. I think we've done this one multiple times already. Oh, look at that. All of this now is a -1 charge. Oops. And this is where your -1 charge is. However, what do we need to do? Probably do some Lewis dot structures. So let me erase this. See, we can alternate a couple of these. So let's try one. Keeping the lone pair on the chlorine the same. Oops. There you go, that's better. Alright, looks like that's all the alternating we can do. So, alright, that's the Lewis dot structure, best structure for it, etc. Blah, blah, blah. Alright, if you have any questions, please let me know. Thanks, bye.